Hi, it's Tuesday, June 23rd, 2020. My name is Noah Seeley, and welcome to my channel. So today we're going to be finishing our discussion of the Deep Reinforcement Learning with Double Q Learning paper by the Google Deepmind research team. We'll be covering the double DQN results and discussion sections of the paper today. Before we get to it though, if anything related to reinforcement learning still seems a little bit fuzzy, I invite you to go check out my two-part intro to reinforcement learning that I'll link in the description below. They're quick videos and cover the definitions, processes, and applications used in reinforcement learning. So as we saw yesterday in the part 1 video of this paper, the Q-learning-based DQN agent is flawed in the sense that it overestimates action value functions, which leads to an optimism that may lead to inaccurate information of states and actions, ultimately resulting in a suboptimal policy for the agent. The paper showed this occur in various examples shown here in figure 2 of the paper. The paper goes on to find that this overestimation occurs because the max function is used while both selecting and evaluating action value estimates. To combat this, the double Q learning algorithm decouples the selection and evaluation by not using the max function during evaluation of the values. The double Q learning will rather learn two separate value functions with their own set of parameters, with each experience randomly updating one of those two functions. For evaluation, one set of weights taken from the value function will determine the greedy policy, and the other will be used to determine the value. If you want more of a review on any of that, go check out part 1 of this video, which I've linked in the description below. And without any further delay, let's go check out the rest of this paper. So this part's going to start with the double DQN section. The double DQN section states that after this pseudo decoupling of the max operator, another value function must be chosen. They say that the target network of the original DQN agent, as mentioned in the background section, is a natural candidate. Thus, now the greedy policy is followed by using the online network, and the target network is used to estimate its value. They refer to this addition to the DQN agent as the double DQN. So following that explanation of double Q learning, we're going to use the agent's online network for selection and the target network as evaluation. They say that this is actually a very close implementation to the original DQN agent, just it should yield the benefits that the double Q algorithm has to offer. So far the researchers built up all this theory of where this overestimation was and found a solution to it. They then implemented the solution to their already built agent. The results section is where all of this previous work is now put to the test. So let's see how it turned out. The researchers used the same tests as were seen in the Playing Atari Games with Deep Reinforcement Learning paper, using the Atari Games benchmark to train one agent to learn many games, all with a single set of hyperparameters. As for the results themselves, for starters, let's look at figure 3 shown here in the paper. The top row of graphs tells us that the original DQN agent was definitely overestimating its value functions. The functions should be closer to their true values, shown with a straight line of the same color across the x-axis. Another observation they found is that the orange lines, representing the double DQN agent, are also consistently higher than the blue lines. This difference, along with the fact that the blue lines are always closer, indicates that the double DQN agent not only reduces overestimation, but also creates better policies compared to the original DQN agent. The middle and bottom row of the graphs show the estimations and their performances. We see that the original DQN estimates higher, but performs lower compared to the double DQN. This contradiction helped the researchers show that this overestimation is indeed contributing to the suboptimal policies shown in the original DQN agent. It's mentioned that observations such as these were found consistently across all 49 Atari games the two agents played on. The section goes on further to discuss how the double DQN agent was able to consistently outperform the original DQN agent. Figure 4 shown here in the paper shows just how much of an improvement there was between the two agents. Noteworthy improvements include the games of Roadrunner, Asterix, Zaxxon, and Double Dunk. The section ends with the team discussing how they were able to show just how strong of an agent they created and how it would be able to generalize itself to learn to play games given various starting points or situations to play from. They obtained 100 different starting points sampled from each game by a human expert and observed agent performance given each of them. In the end, the trials were able to show off the robustness of the double DQN agent, saying that it could generalize very well across many situations, and that this was appealing as it brought them a little bit closer to finding general solutions to the problems they set out to solve. So finally, the discussion section nicely summarizes everything that had been done throughout the research for this paper, and I'll do do my best to summarize all of that here. So if we forget all of the very technical aspects of the paper for a second, the important takeaway here is that the researchers found a problem with the original DQN agent, which was overestimation of value functions that led to suboptimal policies. They identified the root of the problem, the max function being used for both selection and evaluation of the value function estimates. And what they did was fix this problem. They found an algorithm that decouples the max function and then found an implementation of it that they could use on their agents, which actually used tools that the agents had all along. So it's interesting that we can see here the kind of process the researchers had to improve their agent. The important takeaway from the results section is that it all worked out. The double DQN agent was able to create better policies in Atari game compared to the original DQN agent, which at the time was considered state of the art. And the double DQN agent was able to do this as hypothesized by reducing the amount of overestimation in order to create these more optimal policies. So yeah, that concludes our discussion of the deep reinforcement learning with double Q learning paper by the Google DeepMind's team. I hope you learned just as much as I did from this piece of literature. Once again, if you still haven't checked out part 1, I've linked it in the description below. There are also more technical bits in today's sections that I did not delve as much into, so as always, I've linked all resources that I've used in the description below for you guys to check out yourselves. If you feel that I've missed anything or got anything wrong, please let me know in the comment section below. That's all for today. Thanks for watching. See you tomorrow.